Okay, this is the second to last problem on the diagonal force worksheet that we've been working on in class, in case your class didn't get to finish this. Okay, so we have this inclined plane with a 5 kilogram mass on it. Okay, so let me get a pen. Okay, so let's draw the forces on this object. We got weight pointing downwards. The weight equals mg, the acceleration due to gravity. So the weight equals 5 times 10 is 50 newtons. What other forces do we have? Okay, unlike the previous problem, we have friction. So object could be sliding down this ramp. And if it is, or if it's at rest, it could be sliding down. And so there has to be friction opposing that velocity, which would be down the ramp. So the friction has to be up the ramp. Okay, we also have normal force, but don't draw the normal force like that. Okay, don't draw the normal force like that because it's not perpendicular to the surface that the block's on. So, draw it perpendicular to the surface, like that. Let's draw that black. Okay, that's the normal force. Okay, so we got 3 forces in this free body diagram. Now, what we're going to do is, remember on inclined planes, we got to look at it differently. We got to look at the XY axis like this. And we tilt that XY axis. We tilt that XY axis so it's like a cross, an upright cross. So let's redraw. Okay, so we got normal force pointing up. We got friction pointing to the right. Okay, see, I tilted it. We got the weight not going down, but tilted to the left. If I tilt the cross, it goes with the cross. So, now, see this angle right here? Here, let's call that weight. See this angle right here? The inclined plane angle. Okay, that's always going to be the angle between the y-axis and the weight. Always. I can show it to you geometrically why, but just take my word for it. So, if you have a slanted force and the angle is somewhere else, and you need to realize that angle is always between the slanted force and the y-axis. So the 37 is right there. Okay, whenever you have a slanted force, first thing you want to do is to break it up into its x and y components. 3-finger rule. So there's wy and here's wx. So 3-finger rule. Now, I think the first question was, what's the weight? We found it there. My next question is, what's the normal force? Well, let's find out what wx and wy are first. I'm using my qx equation is q times cosine of theta. And qy is the other one, q times sine of theta. Now, if you're going to use my equation, my qx and qy equation, it's always for the angle from the x-axis that these are for. These ones that I gave you. Always, they only apply if the angle's from the x-axis. If it's from the y-axis, you'd have to switch these two things around. Okay, so So I need this angle to plug into these equations. The angle from the x-axis between the weight and the x-axis. So that would be, let's see, 90 minus 37 is 53 degrees. Okay, so let's do it. Weight is 50, cosine of the angle from the x-axis, 53. Then the other one, 50 times sine of 53. Okay, let's do that. So we get, for the cosine, we get 30, and for the WY, we get 40 newtons. Okay, so what is the normal force? What's the calculated value? Well, look at this picture right here. Look at this picture right here. Right here. The free body diagram. The normal force has to be equal to, it has to balance out. There's no vertical acceleration of the block. There's no up off the ramp or into the ramp acceleration. So the normal force, the upward force has to equal the sum of the downward forces, and there's only one. So isn't it true? Because there's no acceleration vertically, there's no net force vertically, the forces are balanced. So right there. So the normal force is equal to WY, which we already found is 40 newtons. Okay. 40 newtons. Okay, so now we have to find what the friction is. Let's continue over here. Okay, so the friction is equal to the coefficient of friction times the normal force. So there's two kinds of friction, static and kinetic. So when we do static, it's the maximum static friction in that equation. So that'd be mu s times normal force. This would be mu k for kinetic times normal force. Now, you use static if it's at rest, the block's at rest. You use kinetic if it's moving. Well, how do I know this block right here is moving or at rest? That's what we're going to do right now. But first of all, let's find what Fs max is. Okay, so mu s was given over here. The coefficient of static friction is 0.8. Normal force is equal to Wy times 40. So that's going to come out to 32 newtons. Okay, and then mu k is 0.6. So 0.6 times 40. That's going to come out to 24 newtons. Now, go back to your diagram right here. We're looking at the horizontal part right now because we already dealt with the vertical part. So is this balanced or is this unbalanced? That's what we're asking. So I'm going to just draw the block on the ramp. We got friction this way. We don't know which one to use. And we got friction Wx that way. We already found Wx is 30 newtons. Okay, now think about it. What is the maximum static friction is 32. So what if we put If we put 32 here, it wouldn't be balanced, but it's at rest, and that would make sense. So that's the maximum static friction. You can have static friction less than the maximum static friction. In this case, that's what's happening. The static friction, okay, so if Wx is greater than the maximum static friction, the object is moving. Is accelerating. And the friction is Fk, not Fs. Okay, if Wx is less than Fs max, the object's at rest. The box is at rest. And therefore, Wx equals the friction static. No, not necessarily the static maximum, but it could be anything between 0 and the static maximum friction. So obviously this is at rest now because Wx, which is 30 newtons. 30 newtons is greater than, here, Wx is less than Fs max. Fs max is 32. 30 is less than 32. So the object is at rest and Wx equals Fs. So the friction is friction S, and that equals the 30 newtons. Okay, because if it's at rest, the forces have to be balanced. So it can't be 32, it's something less than 32 if it's at rest. And that would be 30 newtons. So, no, this thing's at rest, and the friction is 30 newtons. Okay? That's what you do on these. Okay, if it was moving, you would use, the 24 newtons. And then we're going to do that on the next problem. Okay? So that answers all that. Okay. The last question I have shown over here on the right. Sam pulls a 30 kilogram box up a 19-degree incline, okay? So let's draw the picture. Here's the inclined plane. This is 19 degrees. Here's the box. Sam's pulling it upward. Let's call that tension. He's using a string. Okay. The coefficient of friction is 0.20. So let me write that over here. Coefficient of kinetic friction is 0.20. So I'm assuming this is moving. That equals 200 newtons. Okay, so draw a free body diagram of this box. Calculate the weight of the box. Calculate normal force. Calculate friction. Calculate net force. Calculate the acceleration of the box. Okay, so let's draw a free body diagram. So remember, we make the x-axis like that, and the y-axis perpendicular to the surface. So when I draw it like this, the tension is going to go that way. The friction is going to be going this way. I know it's kinetic friction. The normal force is going up. Should have drawn it over here. And the weight is going to go straight down on this actual picture on the left. And what I just said, the angle will be between the weight and the y-axis there. So when I straighten out that x, that cross, I'll have it slanted like that. Okay, so there's my weight. Okay, so what I'm going to have to do is find the x and y components of the weight. Okay, there's wy, and here's wx, not to be confused with fk. Okay, so don't confuse that with your fk. Okay, so that is wx. Okay, the weight was, I forget, hold on. Okay, the weight is mg, which is 30 kilograms. That was given. I forgot to write that. The box is 30 kilograms, so 30 times 10 is 300 newtons. That's the weight. Okay, so Wx, the part of the force, that weight that's dragging it back down, the ramp is equal to W cosine of theta. But remember, you gotta use the angle from the x-axis, which is, see, 90 minus 20, which is 71 degrees. Okay, so Wx is equal to the weight, 300, times cosine of 71 degrees. Let's do Wy while we're at it. Wy equals W sine of theta. So that's 300 sine of 71. So there's my x and y components of the weight. So like in the previous problem, the normal force is going to equal, it's going to be balanced out by the y component of the weight. So in letter C, they say calculate the normal force acting on the box. So normal force is equal to Wy, is equal to 284 newtons. Okay, now they're asking calculate the friction acting on the box. That's letter D. So the friction, they gave me the coefficient of kinetic friction. So kinetic friction is mu times n if you use the kinetic coefficient. So this would be 0.2 times that normal force that we just found. Normal force is 284. So the friction is going to be 56.8. So 57 newtons. So calculate the net force on this block right here. So looking at your free body diagram, we got the block, we got the tension going this way. Oops. We got the friction going that way, but don't forget that you also have the x component of the weight going to the left as well. So look at this picture right here. And you can see that. Okay. So we have WX and FK both going to the left, two separate forces. FK and WX. So the net force in the horizontal position would be, let's put all these terms in. Tension, did they give me the tension? I didn't write that in. It's getting pulled with a force of 200 newtons, so I should have put that before. So tension is 200 newtons. The friction is 57. And the X component is 98 newtons. So the net force is going to equal the tension minus the friction minus the WX. So that equals 200 minus 57 minus 98. So net force is 200 minus 57 minus 98, and get 45. So that's my net force. Now to calculate the acceleration, I'm just going to use Newton's second law of motion. Net force equals ma, so 45 equals the mass. The mass is 30 kilograms times the acceleration. So the acceleration is 45 divided by 3, 30. So 4.5 divided by 3, 1.5 meters per second squared. That would be down the ramp. I'm sorry, that would be up the ramp because the tension's greater than the friction in WX. It could be down the ramp if the friction in WX was bigger. At least that would be the direction of the acceleration. Okay, so that should do it.